Hey everybody, welcome back to Pre-Calculus. We are here in Unit 7, Lesson 13. So this is the final lesson for this unit, and the learning target is that we want to solve trigonometric equations using identities and algebraic manipulations. So first off, we need to review inverse trig functions. So on a regular trig function, if I asked you to find something like sine of, say, pi over 6, I'm giving you the angle, and I'm asking you to find the sine of that angle, or the y-coordinate on the unit circle. And that, of course, would equal 1/2. When you're evaluating an inverse trig function, you are going in the opposite direction. So the argument of the inverse function would be the y value or the x value or one of those ratios, and you're being asked to find the angle that goes along with it. So the first example here, we have the inverse sine of 0. So this is telling me that the sine of my angle is 0, or in other words, the y-coordinate is 0. So I'm looking for what angles on the graph give me a y-coordinate of 0. And there are two of them. One right here at an angle of 0, and another one over here at an angle of pi. So these ones may have more than one correct answer. In this case, the inverse sine of 0 would be either 0 degrees or 0 radians or pi radians. And the next one is asking us for the inverse cosine of -√2 over 2. So I know that the cosine is -√2 over 2. In other words, the x-coordinate is equal to -√2 over 2. And I'm being asked to find the angle, or the inverse, that goes along with that. So x-coordinates of -√2 over 2. I see that up here at an angle of 3 pi over 4. And I also see this down here at an angle of 5 pi over 4. So the inverse cosine of -√2 over 2 is going to be equal to 3 pi over 4 and 5 pi over 4. Now tangent can be a little bit trickier because the tangent isn't just one coordinate. It isn't just the x-coordinate or just the y-coordinate, but it is the ratio of both. I know that tangent is y over x. So if I'm finding the inverse tangent of -1, I'm asking myself what angle gives me a y over x ratio of -1. And if a ratio is -1, a number divided by itself is 1. That tells me that y and x are the same number, but they have opposite signs. So same number, so that when you do y divided by x, they cancel out and give you a 1, but opposite signs so that you get that negative involved. So I'm looking for places on the unit circle where y and x are the same number, but one is positive and one is negative. So I see that up here, x and y are both √2 over 2, but in this quadrant the x value is negative and the y value is positive. So that's that angle of 3 pi over 4 again. And I also see this down here, where x and y are both √2 over 2, but the y-coordinate is negative. So that'd be an angle of 7 pi over 4. So the inverse tangent of -1, the places where the y to x ratio is -1, happens at an angle of 3 pi over 4, and it also happens at an angle of 7 pi over 4. Another example with tangent would be the inverse tangent of -√3. So again, tangent is the y to x ratio. Y over x is -√3. Well, that's not even a fraction, but I can write it as a fraction, put it over 1. So I'm looking for places on the unit circle where the y value is -√3 and the x value is 1. Problem is, we don't have any of those. There is no spot on the unit circle that has a y-coordinate of -3. Every single one of these unit circle angles has a denominator of 2. So if we want to match something that's on the unit circle, I'm going to need a denominator of 2. So I am going to take both the y and the x coordinates here and divide them by 2. That's fine as long as I do it to both the top and the bottom of the fraction. And now this is something that we can locate and match. I'm looking for a spot where the y-coordinate is √3/2 and the x-coordinate is 1/2. And again, because of that negative sign, one of them is going to be positive and one of them is going to be negative. So I'm looking for a y value of -√3/2 and an x value of 1/2. That happens right here at an angle of 5π/3. Alternatively, we could have the y value be positive and let the negative sign come from the x coordinate being negative. So that would give us a second option of 2π/3. So the angles that give us a tangent of -√3 are 2π/3 and 5π/3. So if you feel like you need some more review or some more practice with this concept of finding inverse trig functions using the unit circle, you can go back to Unit 5. We had a whole lesson on that and a whole homework assignment that you can review if you want to. But now we are going to move forward and use this skill of finding inverse trig functions to solve equations. So a way that you can think about this is that if you were solving the equation 3 times the log base 4 of 2x to the 5th equals 45, you would first isolate the logarithm. So you would try to get the log base 4 of 2x. You would try to get that all by itself, and then you could exponentiate both sides. The inverse of a log base 4 is 4 to the power of whatever your argument is. So you could undo the logarithm by using an exponential. If you were solving the equation 3 times the square root of 2x plus 4 plus 6 equals 60, your goal would be to isolate the radical. You would get this 2x plus 4 all by itself, and then you could square both sides to undo the square root. And this works because logs and exponentials are inverses of one another, and square roots and exponents, like squaring both sides, are also inverses of one another. So if you have a logarithmic problem, the inverse is an exponential. If you have a square root, the inverse would be squared on both sides. If we have a trigonometric equation, then the inverse is simply called the inverse trig function. So something like inverse sine or inverse cosine or inverse tangent. So if you're given a trigonometric equation to solve, you will need to isolate the trig function and then take the inverse function on both sides of the equation. So let's look at some examples here. The first one I have is 2 sine of x minus 1 equals 0. So I'm trying to isolate the trig function. I'm trying to isolate the sine of x so that I can use the inverse on both sides. So to do that, I need to get rid of the 2 and the -1. So I would add 1 to both sides, and that would give me 2 times the sine of x is equal to 1. And then I would divide both sides by 2, and get sine of x is equal to 1/2. So here, if I'm trying to solve for x, right now I have sine of x. What I need to do is use the inverse sine function to cancel out the original sine function and get x by itself. So I would take the inverse sine on both sides of the equation. And then the inverse would cancel out the sine and leave me with x alone being equal to the inverse sine of 1/2. And this is what we were just looking at the beginning of the lesson. I know now that my sine is 1/2. In other words, my y-coordinate is 1/2, and I'm looking for the angles on the unit circle that make that so. So a sine value or a y value of 1/2 happens right here at pi/6, and it also happens over here at 5 pi/6. So x is equal to the inverse sine of 1/2, and that is equal to the angles pi/6 and 5 pi/6. So I got the sine function by itself, took the inverse of both sides, and then used the unit circle to figure out what the inverse sine function was actually equal to. Another example here, I have tangent squared of x minus 3 equals 0. So again here I need to get the trig function alone. So I would add 3 to both sides, and that will give me the tangent squared of x is equal to 3. And I don't just want tangent squared, I want tangent alone. So I'm going to take the square root on both sides. And that will give me tangent squared of x is equal to, not tangent squared, just the tangent anymore, that was the whole point, is equal to plus or minus the square root of 3. So that's the tangent of x, but I want x alone. I want to get rid of the tangent. So I'm going to do that by taking the inverse tangent on both sides of the equation. So the inverse tangent will cancel out the regular tangent and leave me with x is equal to the inverse tangent of plus or minus root 3. So again, now I need to use the unit circle to evaluate what is the inverse tangent of plus or minus root 3. I know that the tangent is the y/x ratio, so I know that my y/x ratio is going to be either positive or negative root 3. If I want to write that as a fraction, I could put it as root 3/1. And now if I want this to match something that's on the unit circle, it's going to need a denominator of 2, because all of my x and y points on the unit circle are over 2. So I'm going to put both the numerator and the denominator over 2. So what I'm really looking for here is places on the unit circle where the y value is root 3/2 and the x value is 1/2. And it can be either positive or negative. So I'm going to be finding all the spots where that works. So a y value of root 3/2 and an x value of 1/2 happens there. It happens over here at 2 pi/3. It happens down here at 4 pi/3. And it happens over here at 5 pi/3. Y value of root 3/2, x value of 1/2, either positive or negative. So that gives us actually 4 different answers here, 4 different angles of x that make this equation true. It can be either pi/3, 2 pi/3, 4 pi/3, or 5 pi/3. Alright, so for problem 3 here, let's take a look at a slightly more complicated example. And the difference with this one is that we have not one but 2 different trig functions. So our step of isolating the trig function is going to involve some factoring to see if we can get these separated. So when you have 2 different trig functions in the problem, similar to you would with your verifying identities problems, we're going to look for a greatest common factor. I have 2 different terms here, and I see that there is a cosine of x common to both of them. So I'm going to factor out that cosine of x and then be left with sine of x minus 2. And this all equal to 0. Now, if you recall your zero product property, a little bit of algebra and factoring review here. If you have something like x plus 3 times x minus 2 equals 0, these two numbers multiplied together equal 0. So we can split this up into two pieces. Either x plus 3 is equal to 0, in which case x is negative 3, or x minus 2 equals 0, in which case x is 2. And the same thing works if you have more than two different factors, or if you have something like x times y minus 2 equals 0. If you have the product of two things that multiply together to equal 0, then either of the factors individually equals 0. So in this one, either x is 0 or y minus 2 is 0, in which case y is positive 2. So looking at my trig function here, that's exactly what we have. We have two different terms, cosine of x and the sine of x minus 2, both of which are set equal to 0. So I can split this up into two separate equations based on that zero product property. Either the cosine of x is equal to 0, or the sine of x minus 2 is equal to 0. So now we can take those one at a time. If cosine of x equals 0, well, that's already got the trig function isolated, so I can just take the inverse cosine on both sides. Cosine and inverse cancel out, and then you'll be left with x equal to the inverse cosine of 0. So remember that cosine is looking for the x-coordinate. So we're told that the x-coordinate here is 0, and we're looking for what angle would give that. X-coordinates of 0, I see that up here at pi over 2, and down here at 3 pi over 2. So the inverse cosine of 0, that gives us solutions of pi over 2 or 3 pi over 2. But then we also have to consider this second branch of the problem, the sine of x minus 2 equals 0 branch. And so here, to isolate the trig function, to get sine of x by itself, I would add 2 to both sides and get sine of x is equal to 2. Then to get rid of the sine and just have x alone, I'm going to take the inverse sine of both sides. And that would give me x equal to the inverse sine of 2. So sine is the y-coordinate. I'm looking for places on the unit circle where the y-coordinate is equal to 2. Problem is there aren't any. The biggest value of a y-coordinate that we have would be y equals 1. So this branch actually has no solutions. There are no angles that give you a sine or a y-coordinate of 2. So my only answers here are x equals pi over 2 or 3 pi over 2. So let's look at another example that is somewhat similar. The first thing that I would do on this one is get all of the stuff on the same side of the equation. So if you had a problem that was something like xy is equal to 2x, we want to set this equal to 0. So I'm going to subtract 2 cosecant of x from both sides of the equation so that I have secant of x times the cosecant of x minus 2 times the cosecant of x, and that's equal to 0. And now, similar to the previous problem, when you have two different trig functions, in this case secant and cosecant, we want to isolate each one of them individually. So to do that, I'm going to do some factoring. I see that both of these terms have a cosecant in them, so I'm going to factor out cosecant of x, and then I am left with a secant of x and a minus 2. And since these two terms multiplied together equal 0, that means that either term individually is 0. So either cosecant of x is equal to 0, or the secant of x minus 2 is 0. Now, we're not real comfortable finding inverse cosecant or inverse secant of a number. So if you have anything other than sine and cosine, go ahead and use a reciprocal identity. So if cosecant of x is 0, then the reciprocal identity tells us that cosecant is 1 over sine. So if cosecant is 0, then the sine is the reciprocal of that is 1 over 0. So that's undefined because we can't ever divide by 0. This branch of the equation isn't going to give me any solutions. But for the other half, where I have secant of x minus 2 equals 0, I could add 2 to both sides. Get secant of x is equal to positive 2. And now let's use a reciprocal identity. If secant is positive 2, then cosine is the reciprocal of that, is going to be 1/2. And this is starting to look like something that we can solve using the unit circle. If cosine is 1/2, then I take the inverse cosine on both sides. Cosines cancel out, and we have x equal to the inverse cosine of 1/2. So I'm looking for angles that give me an x-coordinate or a cosine of 1/2. I see that here at pi over 6, and, oops, no, that's the y-coordinate. I need an x-coordinate of 1/2 because this is cosine. So that would be pi over 3. And then down here at 5 pi over 3. So my solutions would be pi over 3 and 5 pi over 3. So if you have a problem with more than one trig function in it, you are likely going to need to do some factoring and then split it up into pieces using the zero product property. If you have a problem that has secant or cosecant in it, you are likely going to need to use a reciprocal identity. So problems 5 and 6 are designed for you to try on your own. So go ahead and pause the video here, see if you can figure these ones out on your own, and then hit play to see my work. And here are your solutions for problems 5 and 6. In problem 5, we need to isolate the tangent function. So I start off by adding 3 to both sides of the equation, and then dividing both sides by 3, and we get tangent of x is equal to 1. Then if you take the inverse tangent on both sides, you get x is equal to the inverse tangent of 1. Remember that tangent is the y over x ratio. So if tangent is 1, that means y over x is 1. And if a ratio is equal to 1, that means that both the numerator and the denominator have the same value. So this means that y and x are the same number. That happens on the unit circle here and here. So you have a tangent of 1, or y over x ratio, where both numbers are the same, at pi over 4 and 5 pi over 4. So those are your solutions right here. For problem 6, isolating the sine function, we add 3 to both sides, and then divide both sides by 4, and end up with sine squared is equal to 3/4. So to get sine by itself, you take the square root of both sides, and you end up with the sine of x equal to plus or minus root 3 over 2. Then to get x alone, you take the inverse sine on both sides and get x equal to the inverse sine of either positive or negative root 3 over 2. Sine corresponds to the y value, so we're looking for places on the unit circle where the y coordinate is equal to either positive or negative root 3 over 2. And that happens here at pi over 3, here at 2 pi over 3, and then if the sign can also be negative, down here at 4 pi over 3 and 5 pi over 3. So all four of those angles are solutions to the equation. We have one more practice problem here, and this is cosine squared plus cosine is equal to 0. And this is one that can be factored. They both have cosine in common. So if I factor out cosine, I'm left with cosine to the first, cosine squared divided by cosine leaves it with cosine to the first, plus 1. And that is equal to 0. So when you factor, we have two terms that multiply together to equal 0. That means that either one of them on their own could be 0. So either the cosine of x is equal to 0, or the cosine of x plus 1 is equal to 0. So solving the first half of the equation first, cosine of x equals 0, that's already isolated. So all I need to do is take the inverse cosine of both sides, and I'll end up with x is equal to the inverse cosine of 0. So I'm looking for where the cosine, in other words, the x coordinate, is equal to 0. And I see that up here at pi over 2 and down here at 3 pi over 2. So that would give us solutions of x equal to pi over 2 and 3 pi over 2. And now for the other possible branch of this equation, cosine of x equals plus 1 equals 0. If you subtract 1 from both sides, you get cosine of x is equal to negative 1. And then if you take the inverse cosine of both sides, you get x is equal to the inverse cosine of negative 1. So again, cosine is the x coordinate. We're looking for places where the x coordinate is negative 1. And that happens right here at pi. So x equals pi is also a solution. So my solution set for this whole original equation, x can be pi over 2, 3 pi over 2, or just pi. And those are all possible and all correct solutions. So that's it for this final learning target of Lesson 7. You need to be able to use the unit circle to evaluate inverse trig functions and combine that with your algebra problem solving skills. So that is it for this lesson, like I said, and now you should be ready to try your last homework assignment. See you there.